All right. Okay, so hopefully you've had time to look at those nine energies that I asked you to define and look for examples. So if not, go back to the previous video and remember what I'd said. I was looking for you to just make a table and quickly look at some like a description of those types of energies. We said, remember, energy is anything that allows processes to happen in the universe. So again, this is video 2. Just to go back, this is really weird. I'm sitting in my office talking to nobody, and hopefully you guys out there in the interwebs are staying safe, and hopefully this will help you get through all this weirdness. Okay, so again, we're looking at energy. So let's get going. Okay, so these are the ones I asked you to do. I'm gonna go now and talk about them a little bit here. So let's talk about energy. Let's see what we got here. So I made a table as well. Um, Again, so these are the 9 that I gave you. Let me reach back here and get my stuff. Excuse me. So thermal energy, the first one, energy. Thermal means heat, right? So thermal energy is just heat. So anytime we talk about thermal energy, we're talking about how hot something is in terms of how much energy is inside of it. Okay, so when things are hot, right? Hotter things move; their atoms move faster. So when we talk about a liquid, let's say a hotter liquid, the atoms are able to sort of move around each other more, right? So they have more kinetic energy. Kinetic energy is the energy of motion, and their average. Carefully, average. This is a probabilistic idea involving probabilistic probability, right? So their average kinetic energy, the most likely energy that they could have, is their thermal energy. Hotter things move around more. So a liquid, all the atoms are able to move around. In a solid, they're wiggling. So really cold solids wiggle a very small amount. Hotter ones move around a lot more, and we get them so hot, all of a sudden they change phase. They become a liquid. So all their atoms start to move around each other, and they become a liquid. So ice, all the ice crystals, are wiggling around in there, and then they wiggle around so much energy, they start to move around each other, and then they get so hot that they become a gas. They move around. So the hotter it is, the more energy each of their atoms have, right? And this is probabilistic, right? So when we talk about that, we mean the most likely energy. So here, one second. Let's draw a graph here. I got my my Paw Patrol little thing I can draw on here. So if I do a graph of um, energy, let's call it K. Okay, let's call it K, and this is frequency. Okay, the amount of that it has. So if I take a sample of, let's say, a glass of water, okay, its energy will look like this. This is called a Boltzmann curve. So this here, over here, that peak at top of it there, okay, that's its highest amount of energy. Okay, so that gives us its temperature. All right, so this is let's say it's a glass of water. This is its room temperature. Okay, so that we can use this idea here to give it an idea of temperature, right? However, since it's probabilistic, there's going to be some atoms that are super cold, that aren't moving around much, and there's some atoms that are super fast. So let's say we put a cutoff temperature here of its boiling point. So there's always going to be a certain fraction out here of of atoms in this glass of water, let's say, that have a temperature or energy higher than boiling. So this is why when you have a glass of water sitting on a table, it'll eventually all evaporate because some of its atoms, right? Some of its atoms there'll always be a certain amount of its atoms here in this range. And as the amount of stuff reduces, we get this curve will just get smaller and smaller. But there'll always still be this section where that shows how many atoms have enough energy to get there to get released by the glass of water. And you leave long enough, all the water will be gone away. Okay, so just to give you an idea of this being probabilistic. Also, another thing, this curve, okay, this curve here. I apologize for the exposure problems, but if we get things hotter, it changes the peak, but also changes the shape a little bit. So if I got it hotter, it actually just spreads out the curve. Okay, so we still have stuff here. It's still probably, it just becomes a wider We call this a Boltzmann distribution. Very important for quantum mechanics. We'll talk about in the grade 12 course later. Okay, so just for that's to give you an idea of energy in terms of thermal energy. Thermal energy is fun because it's the energy that all things have when they sort of, we'll talk about the second law of thermodynamics. We'll get there. For example, what do we have here? We have things like fire, right? Things are hot, right? So all their atoms are moving a lot, and if you put your hand near that, those atoms that are moving a lot are able to interact with you, so they bounce off of you. They have a sort of a collision. Like hot air molecules come and collide with your hand and transfer some energy to you, so your hand becomes warmer. Okay? Another one, hot air rising because it's lower density, because the air molecules move a lot faster around each other, so they're able to space out more, and then they go up. Cold air sinks. They're lower density. The air molecules don't move around as much. Okay. Next one, that's electrical potential. Electrical potential energy is energy of electricity. Right? We have electrons moving around in a circuit or something. They're charged. Hopefully you remember they're negatively charged. Each atom has a negative charge from its electrons and a positive charge from its protons. And the law of electric charges says that opposite charges attract. So a plus and a minus will want to attract each other, and a plus and a plus will want to pull away from each other. Negative and will want to pull away from each other. So we can have a charge distribution on something, and these will produce electric fields, and that will cause things to move. So it causes electrons to flow through a circuit, or whenever I rub a balloon to my head and I can stick it to the wall because the whole thing becomes charged, and can just stick there, right? That's electric potential. Electric potential is anytime we have electricity, electrons having charge, and the charges want to interact with each other in some way, and they push on each other, repel each other, or attract each other, or do something like that. For example, what examples I have here? 9-volt battery. So when we say volts is a measure of the amount of energy per coulomb. Hopefully you remember from grade 9, maybe, I'm not sure. But if we remember from grade 9, a volt tells you how much energy is measured in joules. I don't think we've talked about that yet. Good thing to remember. Here, let's write that down. That's a good one. Okay, 1 joule. Okay, 1 joule. What is a joule? This is a little bit weird. It's equals 1 Newton. Any guess? Newton meter squared per second squared. Okay, that is how we measure energy. Things have, where is it? There it is. Energy has units of joules, which is a Newton meter squared per second squared. That's how we measure energy. Okay, so a 9-volt battery, it tells us that every coulomb is just a big chunk of electrons, 10 to the 28 electrons or something, and each of those coulombs, 18, apologies, they have 1 joule for each one. So the higher the voltage, the more energy each group of electrons actually has. Right? AC current's the same idea. It's cycling back and forth like a nice sine wave, 60 times a second. Remember, we use the trigonometry up and down. So it does that 60 times a second. The voltage changes between 120, negative 120, plus 120, negative 120, and it goes back and forth. And it allows us to have light, has computer, all this junk around me. Okay, right? That's electrical potential energy. Okay. Let's move on. Nuclear potential. Nuclear potential energy is that strong nuclear force. When we talked about those 4 fundamental forces, there are gravity, electromagnetism, strong and weak nuclear force. And the strong nuclear force, we said, is these gluons that hold together a nucleus. So, for example, I'm made out of a bunch of carbons. I have 6 protons and 6 neutrons, and they're all stuck together in this tiny little grain of sand. Not grain of sand, 10 to the negative 15 meters. It's a femtometer, small little thing, and they're being held together there. And that strong force holds them together and is a very, very strong, powerful force on that incredibly small distance. It doesn't exist outside of the nucleus. It's a very weird idea, and it's well beyond the spectrum of this course. It's called quantum chromodynamics, that shows us how nucleons, or baryons in this case, they actually are able to talk to each other using these gluons. And when you change um, an atom, so a nucleus, right? When you change something, let's say it falls apart. Let's say in a nuclear reactor, you go to a nuclear reactor, go down to Pickering or something like that, and it's taking uranium 235. So it's a uranium that has 235 protons and neutrons, and it's making it fall apart into two separate new nuclei. So not the atom falling apart, the nucleus itself, this tiny little thing in the center of it that has all the mass, goes from being a uranium nucleus to two separate pieces. And when it does that, it releases energy because it takes less energy to hold together these two than this one. When it's such a big nucleus, it has 235 of these nucleons all held together. It requires a lot of energy. And then when it falls apart, it requires less energy. There's a difference in energy. And when that difference of energy ends up being released, a conservation of energy. We can't create energy, destroy energy. It's called the first law of thermodynamics. We'll talk about it later. But this idea that we have a held together nucleus, this 235 things, and then they fall apart. It takes less energy to hold the smaller ones together. So that energy has to go somewhere, it's released. You do this enough times, you put a bunch of water around it, it collects the energy, or not water, some sort of coolant, it collects the energy. We boil water to turn a turbine, we have an electrical power plant. That's a nuclear reactor. It happens in the sun. It's the opposite in the sun, because instead of a nucleus being held together and falling apart, that's called fission. Fusion is what's happening in the sun right now. So in fusion, we take a hydrogen and another hydrogen, kind of. It's a deuterium, it has an extra neutron, and they smack together and they stick together and they become helium. So we take two separate nuclei, right, of two different atoms, two different types of elements, hydrogen and a hydrogen, slightly different hydrogen, but whatever. They stick together and they become a new helium, and that actually releases energy because it's easier for the atoms to be held together in this two thing. Is this, the atomic number of helium is 2 as opposed to 1 for hydrogen. These two, they come together and we have energy being released, and that's what's happening in the sun right now. The gravitational pull of all those hydrogen atoms smashing into each other are able to stick. They're not able to stick together normally because the electrons around them repel. So I have a hydrogen here and a hydrogen here, and I try to push them together, and then the electrons are fight, and they can't quite touch, do anything. In the sun, because they're moving around so fast, there's so millions of degrees Celsius, they're able to smack into each other, such that they fuse into a helium, and when that happens, it releases energy. Okay. So this is when we change we move around on the periodic table. So from hydrogen to helium, or from uranium to like lead or something like that, we breaking apart, fission or fusion, we release energy, and that's the nuclear potential energy stored in those nuclear bonds between nucleons. That's a fun one. Sorry, I got a little bit excited there. All right, radiant energy, light. Light is just the electromagnetic radiation vibrating. It's these electric fields and magnetic fields going around each other, these sine waves, and that produces light, right? The visible light that we see, the electromagnetic radiation that we can't see, things like radio waves, things like the cell phone signals at 2.6 gigahertz that you're seeing, or the X-rays, which are incredibly high energy and pass right through our bodies. Right? The higher the frequency, the more it goes up and down. Like, for example, radio waves. Radio waves go up and down in the megahertz, so they go up and down 1,000,000 times. Like, you go to radio and you check on the let's say the radio station, 88.5. That's a megahertz, and it tells me that it's 88.5 million times that the electromagnetic field is going up and down. And at the same time, that magnetic field at right angles to that. And that frequency gives us the energy as well. The higher frequency I go, until I can push it up into into the 10 to the 15 hertz. So what would that be? Million, billion times a second. Then we get light, the stuff that we can see. And you all know, if you wear a black shirt on a sunny day, it's going to get hot. So clearly there's energy being absorbed by that shirt from the light. So from the light that's coming from the sun, the visible light that you see is going to get to your shirt. It's black, so black implies that it absorbs all of that energy. It gets hot, right? So as opposed to a white shirt that wouldn't get as hot because it's reflecting it, right? So examples, visible light, X-rays, infrared, that whole electromagnetic spectrum you talked about in grade 10 optics, hopefully. Next one, gravitational potential energy. This is awesome. Remember, gravity is the force that attracts anything with mass, anything with mass in the universe. Okay, Newton's law, universal law of gravitation, tells us that any masses attract. Okay, so that attraction is a potential energy, which eventually turns into kinetic energy, right? Because if I have these two things, they want to pull up closer to each other. There's you sitting on this massive ball of rock called the Earth. You're attracted to it. The modern view of that now is we take the curvature of space-time as opposed to Newtonian flat space-time. Masses, the idea is, let's go back to here. If I have, this is the Earth. The Earth bends space-time. Where are we? Right there. Earth bends space-time. And there's you, and you have a potential to go down towards it. You jump, you increase that potential, and you're being attracted down towards it. Right? So this is a one-dimensional version, sort of a four-dimensional idea of four-dimensional space-time. But don't worry about it. Just know that anything that has mass attracts, and we can actually use this formula here. This is awesome formula that the potential energy is calculated by m, the mass, times gravity times the height. So the gravitational potential energy, we're going to get a U, okay? U for potential. U for potential. Okay, physicists say so. All right, it's mass times G. What's G? Do you guys know what G is? Tell me right now. What's G? Yeah, good. Times the height. Okay, so on Earth, we can say that the potential energy is an object's mass times gravity times height. Now, this is the height from Earth. Okay, so this is an object's mass measured in kilograms. This is 9.81 newtons per kilogram, and this is height above the Earth's surface in meters. Now, does that matter where I'm jumping from? Is it from here? Is it from somewhere else? We'll talk about what that means. This is a relative potential energy. Okay, this is our gravitational potential energy. Okay. Okay. So next, kinetic energy. So kinetic energy is the energy of motion. So we've learned in Newton's first law that things have inertia. It takes energy to stop them from moving. Things that are in motion require energy to stop. So things that are moving have some sort of inherent energy. We call that kinetic energy. It's the energy of motion. So things that move have energy. Okay, so right, Newton's first law, right? Things move. For us, so the object is moving. We have to give it some sort of energy, and we define that by kinetic energy. We're going to call it K equals 1/2 mv squared. Okay, so the kinetic energy is 1/2 times the mass of the object in kilograms times meters per second. Now, what's this going to be? What are the units of K going to be? Well, it's going to be kilograms meters squared per second squared because we're squaring it. Notice this is not a vector quantity because when we square a vector, that removes its directionality. Squaring a vector gets rid of that vector quantity of it. Okay, so when we're actually squaring it, what it's doing is it's basically just taking the magnitude out of it. Right? A moving car has a lot of energy, right? If you get hit by it, right, then that's going to cause some problems. Right? You try to stop somebody who's running at you. Their motion, their mass provides their kinetic energy. Okay. Next, where should we go from here? Elastic potential energy. So storing energy in an elastic. It's anything that has a linear restorative force. This is a weird idea. Anytime I have something in equilibrium, let's say a pendulum. Okay, I have a pendulum on a string. Okay, or even a spring. Let's say if I take a spring. Okay, let's assume I have a wall and I have a spring with a mass on it here. Okay, so I have a spring of a string with a mass. It's at equilibrium. It's not wanting to do anything. If I move it from that equilibrium position, if I take it here and I move it away, it's going to spring back, right? And if that force, if it's elastic, the definition of elastic means that the amount of force of wanting it to pull it back is proportional to how far away I push it from. So if I double the distance that I extend a string, I double the force that it wants to pull back. What happens with that is it ends up producing waves. I let it go. It goes. If I pull it away from its equilibrium position, if I let go, it's going to go back to its equilibrium position. It's going to keep going. It's going to have inertia. And it's going to keep going. And it's going to compress the spring, and it's going to go back to its equilibrium. And it's going to go back and forth. And if there's no damping, it'll do this forever. But there's always going to be energy lost to the outside world, and it'll eventually stop spinning. Okay, so that's elastic. When we store energy in something like a spring or a pendulum, I take a mass on a string and I pull it away from its equilibrium position, I let go, it's going to want to start swinging. Okay, so it's called elastic potential energy. And this can be sound, water, elastic bands, anything like that. Anything that produces waves or wants to go back and forth in some way. A specific example of that is sound. When we have air, so air is a bunch of air molecules. If I push on them, let's say with a speaker or my voice or something, they compress a little bit, and then they want to go back, so they start wobbling back and forth. And if they wobble back and forth between the range of 20 hertz, so 20 times a second, and 20,000 times a second, our ears are able to convert that motion of those, or that vibration of the air, into some sort of signal in our brain, and you can hear me, right? So sound is just a specific example of elastic potential energy in the medium of air. Not always air, right? Sound can travel through walls, right? Sound can travel, it just travels faster, but it's able to travel through different medium. Anytime there's a vibration in the medium itself, and it's between 20 and 20,000 hertz, which is what our ears can hear. Okay. Last one we're going to talk about chemical energy. So this is the energy stored in chemical bonds. Anytime we have an atom stick together to make a compound, some sort of a compound, whether it's molecular or ionic, there's bonds, ionic bonds, covalent bonds, but however holds things together, that's energy. So if I break that apart, if I do something to rearrange the atoms and their bonds, they have to either absorb or release energy. So whenever atoms are rearranging their molecules, right, they're in breaking bonds, they can release energy. If they release energy, it's called exothermic. If they absorb energy, it's endothermic. So, for example, hydrochemical like gasoline, right? Hydrocarbons, sorry. Gasoline has it has 8 carbons and a bunch of hydrogens together. We can break all those bonds up, releasing carbon dioxide and water, right? You react it with oxygen in a combustion reaction. There's a lot of energy stored in all those bonds between all those 8 carbons. Now they've been broken up, they've been rearranged. The carbons now have 2 oxygens stuck to them in a carbon dioxide molecule. So releasing all that energy, when we burn it, it makes fire, right? So gasoline burns because we're breaking the chemical bonds. There's chemical energy stored in the bonds, and then when we break them, they have to go somewhere. They have to release somewhere. Okay? So those are all the ones that we've looked at here. Hopefully this helps. If you have any comments, please use our Discord. I've hopefully got most of you in our Discord. Please ask comments. There should be put it in the SPH3U channel, I think it's called. Still learning Discord. Sorry guys. Okay, boomer. So please use that Discord. Ask anything. You can send me emails, use my Twitter, anything like that. Okay, so I'm going to sign off for now, and hopefully all is well with all you guys, and hopefully you're not getting too bored. If you're too bored, just let's do some physics, okay? And feel free to message me whenever you want. All right.